Good afternoon, professors and judges. We are from St. Paul's College, and today we are glad to have a chance to talk about our research paper about covering a 45-point configuration with disjoint unit disks. Our motivation for this paper originated from an interesting question proposed by Naoki Inaba in 2008. The question asks about the existence of a configuration of 10 points on a plane, such that no combinations of non-overlapping coins can cover it. For example, we chose these 10 points as shown on the screen. We can see that it can be covered by coins modeled as disjoint unit disks, as shown. It is quite hard to find a trivial answer to whether there exists a configuration that cannot be covered, as proposed in the question. But Inaba himself gave an elegant proof using probabilistic methods to show that there does not exist such a configuration. But then the natural question arises, that is, what is the minimum number of points, k, on a plane, such that some configuration of those set points cannot be covered by disjoint unit disks? The question gained popularity in the puzzle community, and several groups made improvements on the bound of k. The most recent advancement on the problem was on a paper written by a team of Alupis, in which they improved the lower bound of k to 11, and provided a configuration of 45 points that they claimed to be the improved upper bound of k. This configuration caught our eye. The team verified the configuration by using extensive computer search, which brute-forced all the possible combinations of the disjoint disks on the plane and checked whether there exists a combination of disks that covers all 45 points in the configuration. This motivates us to try to prove the claim by the Alupis team. Our approach to the problem was to try to eliminate as many configurations of unit disks as possible. We can achieve this by finding constraints on the combination of disks, which means, theoretically, if we found enough constraints, we can find out that no possible collection of disjoint unit disks is able to cover the 45 points. In order to proceed with our results, we first defined the names gamma A, B, and C to represent the innermost, middle, and outermost concentric circles in the configuration. Then let the points on gamma A, B, and C be Pi, Qi, and Ri, respectively. We also state that a circle Ci has a center of Ci, and the number of disks in the collection to be n. We then define the irredundancy of disks in the collection, stating that we can simply ignore any disk that covers no points. Immediately, we can say that if there exists an irredundant covering of disks, n is less than or equal to 7. We proved this using the results in a paper written by the team of Graham. We also define what we mean by adjacent circles, which means putting their angles in order of their polar forms. We then define the configuration matrix in order to systematically consider different combinations of collection of disks. For example, consider our following configuration. We can see that C1 covers 5 points in gamma C and gamma B, and no points in gamma A. C2 covers 7 points in gamma C, 8 points in gamma B, and 1 point in gamma A, while C3 covers 7 points in both gamma C and gamma B, and again no points in gamma A. Hence, the configuration matrix is as shown. From this configuration matrix, we can see that it's essentially a cyclic permutation, and hence calculated that there are over 7.3 trillion cases. Now that we can show some preliminary results from inspecting the problem. Firstly, we can calculate some bounds for the distance between the disk center and the origin, corresponding to how many points they cover in gamma A, B, and C, as shown in proposition 2.2. Then by calculating all the bounds, we can construct the table shown, which the table for gamma A and gamma B can be obtained as well. We also proved that the number of disks used in the collection is bounded to be greater than 2 in corollary 2.3. Obviously, n is not equal to 1, and for n equals 2, they must cover both 10 points and 11 points in gamma C, which by table 1, we can see that they must overlap. So on to the main constraints. We can divide them into two sections: row constraints and column constraints. Firstly, we study the cases for the impossibility of combinations of adjacent disks covering on the same concentric circle in the row constraint section. In Theorem 2.8, we impose an upper bound on the angle between two centers of disks CI/OCJ with respect to how many points they cover in gamma C. We proved that by considering the intersection of the two disks on gamma C, notice that there must exist an RA on gamma C that CI and CJ cannot cover, in which we define a map T that measures angles from a fixed interval. Then by doing some simple algebra, we can obtain the proposed bound as above. By utilizing the bounds on table A, the bounds on table 1 and the bound on the angle, we can create such a table, which shows the impossible combinations that are covered by adjacent disks. Now we show that n is less than 5 in theorem 2.9. For n greater than 5, there must exist an angle CIOCJ that is smaller than 60 degrees. By using the cosine rule and taking bounds from table 1 and lemma 2.4, we can show that both CI and CJ must cover at most one point, which by the table we just shown is an impossible combination, hence proving the theorem. Following 2.8 and 2.9, we are also interested in providing a lower bound to the angle between two disk centers. Hence we proved proposition 2.10, which generalized the two adjacent disks to a collection of adjacent disks and provided this lower bound to an angle to strengthen theorem 2.8. Notice by definition, there exists an RA that the collection does not cover on gamma C. Using the map we defined earlier and following the procedure, we can write this system of equations and by algebra, obtaining the assertion. And using the lower bound we've obtained in proposition 2.10, we can calculate the lower bound on the angle for all cases of adjacent circles. We can define f, c, and m to be the maximum of theta in the bound stated. For example, for the case of two disks covering 1 point and 5 points respectively, then we can find out that fc 1,5 is greater than or equal to 0.826 by using the extreme value theorem. After calculating all fc and m's, we can obtain the following table. Notice we also proved that the sum of all fc and m's of adjacent disks has to be less than or equal to 1. So for example, 3 disks that covers 1.5 points and 1 point respectively cannot be adjacent as shown. Hence we can easily see the configuration matrix that we've shown before is impossible. We can also find a table of values for FB and M and FA and M with similar methods as well. Although the previous proposition result does not cover the cases where none of the disks in the collection intersects with gamma B, we developed proposition 2.11, which states that if Ci does not intersect with gamma B, then there exists a Cj in the collection covering at least 8 points in gamma B, which acts as a remedy. In proposition 2.12, we proved that the 3 circles with 3 points in gamma A cannot be covered by 3 different circles, as if such a case is possible, meaning that there must be an angle between 2 disks that is less than or equal to 120 degrees, which means that 2 disks must overlap in that case. Moving on to column constraints, which is a study on the impossibility of combinations of the same unit disks covering various numbers of points in different gammas. In proposition 2.13, we proved that if a disk covers 7 points on gamma C, it must cover at least 7 points on gamma B. First, we can assume the disk is already covering P0 to P6. Notice the constraint of the disk to cover Q0 and Q6 shown. Pairing with the objective function following the assumption, we can then use the Lagrange multiplier with KKT conditions on these functions, which then we can find that all possible results satisfy the original function, hence proving that disk must cover at least 7 points on gamma B. By calculating other combinations, we can obtain the following table. Finally, we studied the impact of the configuration of certain submatrices on the distance between the origin and the center of the corresponding disk involved. By theorem 2.14, we sharpened the bound of OC with respect to how many points it covers in gamma C and gamma B by considering the 4 outermost points that are covered by the disk in gamma C and gamma B. Based on the objective function and the 4 constraints this time, we then apply Lagrange multiplier with KKT conditions again, and we can find out the minimum distance of OC, which is very useful for strengthening theorem 2.8. At last, by using all the lemmas, theorems, and propositions we have developed, we run computer programs to check how many possible cases were remaining, and find out that for n equals 3, there are 2 more cases left, and for n equals 4, 1,552 combinations are left, and for n equals 5, 455 combinations are left. So in conclusion, we have improved from over 7.3 trillion cases to under 40,000 cases left. This is the end of our presentation. Thank you.